All right, team, we're going to get started with some geologic history. We got this fun little diagram showing some of the fossils and geologic history, which I would like to point out that this is not to scale, and we'll look more closely at this later. You might have noticed it on pages 8 and 9 of your reference table, the last diagram of our Earth Science reference table. How exciting! Geologists use two different ways to express age. One is relative age. So this is the chronological ordering of features, fossils, or events without reference to their absolute age. So you can look at me and you and look at us and say, oh, she's older than I am. You might not know exactly how old I am, but you know that I'm older than you are. Or if you lined up your mom and your grandma together, you'd be able to look at them and tell which one is older. That's relative age. We just know it's older or younger. We don't know the exact age. And then there's absolute age, which is your exact age, an age expressed as a specific amount of time. Always includes some unit of time. Remember your units. So your exact age is your absolute age. We're going to be talking mostly about relative age for this lesson. So geologists have figured out that basically all the things that are happening today have happened before. So nothing crazy happened to put mountains here. Nothing crazy to dig trenches. Everything that's forming trenches and mountains today is what formed those things in the past. So this idea is expressed as uniformitarianism. Say that 3 times fast. Uniformitarianism. It's the concept that the geologic processes that took place in the past are those that occur now. Or, more simply, the present is the key to the past. So this is the idea that there's nothing new. Aliens did not come in the past and put down mountains. It's the same thing that are building mountains today happened before. One of our rules that we're going to use when we look at sequences of rocks is the principle of original horizontality. So this is the idea that rock layers were originally laid down flat and horizontal, parallel to each other. Thinking about sedimentary rocks. How are sedimentary rocks formed? Well, they're formed when sediments get deposited at a lake bottom or an ocean bottom, and then they get built up over time. So you can see in the picture at the bottom, our limestone formed first, then we have our shale, and then on top of that is our sandstone. If we look at our next picture, well, they're not horizontal anymore. So what happened? Well, we know they got laid down horizontally, but since then, something has happened to knock them over. In our last one, something has happened to cause them to get folded and disoriented. But they were horizontal first, and something has happened, probably something like a lot of pressure, to bend them and turn them around. Our next rule is law of superposition, which this is the idea that the oldest rock layers are on the bottom. Here's a fun little video within a video. Law of superposition is just like making a peanut butter sandwich. First you take your bread. It's the first thing. You put it down. Then what do you need? Peanut butter. You put the peanut butter on top. What's the first thing you do? What's the first thing that happens? You got your bread. So that's the oldest thing that's happened. Then you need peanut butter. Then you gotta put your banana on top because that's delicious. So that's the newest thing we've added. What do you add on top of that? I recommend a little bit of cinnamon on top of that. And bam, that's the newest layer. The law of superposition. All right, so that's our law of superposition. So our oldest things are going to be at the bottom because those got placed down there first, and then since then things have gotten placed on top. So we can look at this diagram and look and see which one is the oldest. And you can see that as we go up, these rocks are getting younger and younger. They formed after the bottom layer. Law of original horizontality. What must have happened here? So they were flat, and they've since got pushed up and are now bent and folded over. Then we have our law of cross-cutting relations. Any fold, fault, intrusion, or any of those things that cuts across or affects a rock layer must be younger than that layer. So the layer has to be there first in order for it to be disturbed. So if you take your sandwich and then you cut it in half, well, you first had to have a sandwich there to be able to cut it in half. Or, we put one of those fun little toothpicks in your sandwich. Your sandwich had to be there first. Same is true with an intrusion of rock, usually igneous rock, because that magma can kind of come up into your other layers, or a fault, so where you have the rocks sliding and moving, that's going to be younger. That's going to be newer than anything that happened before. So here's some examples here. So we have our folding happened after everything was put down. And what is older, the granite intrusion or the limestone rock? What do we got here? All right, looking at this, if you look over to the right, I'll move my mouse. So this part right here is a fault. So you can see that these used to match up perfectly, but now they're not because something has shifted these rock layers, and you can see the fault. If we go down, we can see some other examples of faults. This is a good one. You can see that this guy's standing here, and this rock has a fault right here, and these rock used to be lined up, but now it's not. So this fault must be younger than these rocks because it cuts right through it. Ooh, another fault. So again, right through here, this rock is older, and this fault is newer. Then we've got our law of included fragments. Any fragment that is included in another rock must be older than the rock it is included in. So your chocolate chip cookie roll. So basically, you had to have your chips first. You have to have your chocolate chips in order to make chocolate chip cookies. So in order to make a cookie, you need to put those chips in, have them already made, and then make your cookie dough. And we call those broken off fragments xenoliths. So xenolith or xenophobia is like a stranger. So lith is, remember, our lithosphere is our rock layer. So a xenolith is a stranger rock. So here's some examples of some fragments that were found in other rocks. All right, an unconformity. These are important. This is a place in the rock record where layers are missing. What is going to cause a layer to be missing? What causes rock to go away, to get moved away and disappear? I hope you said erosion, because erosion is going to carry away particles, whether from water or wind or a glacier. That's going to carry that rock away and leave you with missing rock record. You don't know what happened there. You just know something happened to carry those rocks away. So in diagram form, we usually see it as this line right here, this kind of like jaggedy, wiggly line. This tells us something happened. And these all got eroded down, and now we're back to our law of original horizontality. And now these are getting deposited on top of them. So here's a real example where you can see that these just end. These layers just end somewhere. They're a little bit folded over and they're gone, which means they must have gotten eroded, and now we have this unconformity. We don't know what other rock layers might have been here. We just know they're gone. Where's the unconformity? Can you find it? Right here. So you can kind of see it's this kind of looks different than everything else. It looks like this part kind of just got cut off. All right, so in our next video, we're going to talk about how we use all of this stuff to figure out what happened in the past. So make sure you don't forget to include